finding the point of intersection of these two lines in 3 space. I like to put these in parametric form. And again, as I demonstrated in the last video, I like to keep my, if I'm going to be solving a system here, I like to keep my variables different, so I replace this t with an s, and I get 0 plus s here as first. I like this situation. Right? Can you figure out why? Why? Get it? Wah wah. Right, so I'm going to use, right, my point now is I've got to decide, right, and then sometimes that makes kids feel uncomfortable. They have to decide what to do from here because there's a lot of ways to do this problem correctly. Since I have x already named as s, I'm going to go over here and call this s, right? So I'm going to say, well, s is equal to -4 plus 2t, and then I'm going to go, what you looking for? To the next equation here, and this equation, the two y equations, and I'm going to say, well, 5 minus 2t must be the same as -7 plus, oh gosh darn it, I forgot my s's up here. -7 plus 3s, but I have s now defined in terms of t, don't I? So I'm going to take, since this expression is equal to s and is in terms of t, and I already have the left side over here in terms of t, I'm just going to plop -4 plus 2t in here. And then I'm going to do algebra 1, right? And my algebra 1's pretty fast. I'm going to leave this 5 over here, but this is going to be -7 minus 12, right? -7 minus 12 is what? -19, right? And then plus 6t, right? So I've done this. I've got -19, but then I'm going to, oh, sorry, -7 minus 12, but then I also have a 6t right here, right? So, but the 6t is going to have this 2t added to it, right? And then I'm going to take this -19 and add it over here. So I end up with 24 is equal to 8t, which means t is equal to 3. So if my t is equal to 3, all I have to do is solve for s, but don't I have an expression where s is alone? Here's s all by itself in terms of what? T. So I'm just going to go and I'm going to say, well, what is s? What is s when t is 3? Sorry, that's a -4, -4. So what do I get? 6 minus 4? So I got 2. Now what do we have to do with this? They asked us for the point up here. A point in 3D space is an x, a y, and a z, not a t or an s. So what do I have to do now? That's right, go up here and say for the t, equations, t was equal to 3. So what is x is equal to negative 4 plus 2 times 3. Hey, I feel like I've done this before. Oh, right, of course. This is going to be what? X is going to be 2, and that makes sense. Check, because x is supposed to be s, and what did I find s to be? S was 2. So let's go down here. Y is supposed to be 5 minus the t value I got, which is 5 minus 6, which is negative 1. Go make sure that the s gives you the same position here. Y equals negative 7 plus 3 times s. I also get what? Negative 1. Check. Lastly, z is equal to negative 1 plus 3, which gives me 2. Double check that over here everything works out, and I get negative 6 plus 4 times s, which is 2, and that's 8 minus 6, which is also 2. So the point of intersection of these two lines is, right, the first line gets to this point when t is equal to 3. The second line gets to this point when t, or s as we called it, is equal to 2. And the point where they meet is when x is 2, y is negative 1, and z is also 2. Let's see what this looks like. Excuse me. So here I am in GeoGebra, and I've plotted the 3 points when it decides to load up. The 3 points and the point and the 2 lines. Just keep saying 3 because it's in 3D. Come on, honey. There we go. See, I just had to be nice. So here's the point, 2, 1, negative 2, and the 2, here are the 2 black lines, right? And this is in 3D space, right? If I flip all this around, right? Whee! Kind of crazy. Did you ever play that? Pick up sticks? Right? That's what this reminds me of. I don't know if anybody plays that game anymore. I'm showing my age. All right. Now we're going to move on from equations of lines to equations of planes. So remember, a plane, right? We often represent planes by these arbitrary, like, kind of parallelogram looking things, right? But remember, they go on forever and ever, right? Right? They go, right? They really go infinitely out in all of these directions. And of course, there are lines in the plane, right? How many lines are in this plane? Oops, sorry. Right? Look at all those lines. Right? Tons and tons, infinity amount of lines in there. So, the standard form for the equation of a plane. Well, first we have to figure out kind of like, well, what do we need? Right? What do I need to know in order to find the equation of a plane? Think about a line, right? Just think about 2D space, Algebra 1. You needed a point, you either needed 2 points or you needed a point and a slope, right? In 2 dimensions. So if I was in 2 dimensions and I gave you a point here, x, y, and I told you the slope or the movement I wanted you to make was the change in y was 2 to every change in x of 1, right? You would go up and over, and there's my line. And you could write the equation of that line with the point and the slope. Now think about when we were doing 2D vectors. Doing 2D vectors, right? You needed a point, I'm sorry, not 2D, 3D. Right, what we were just doing was giving you a point X, Y, Z and having you write right, and let's say I gave you another point here, and I wanted you to write the equation of that vector, right? What did we do? We created, right, you needed the point and the direction vector, which is kind of like your slope, right? Right? So now I want the equation of a plane. So if I want the equation of a plane in 3D, if I give you some point, let's say I give you a point here on the XY plane, let's say Z is, well, let's just call it Z, but if I was actually on the XY plane down here on the floor, my Z would be 0, right? If I want you to be, I want the equation of the plane, right? Well, the XY plane contains that point, but so doesn't, can you imagine, it's hard for me to do this on the screen, but there's a plane that comes down, excuse me, comes down right through it, or another plane that comes diagonally through it. So there's tons and tons of planes that go through this point, not just the yellow shaded XY one that I have. But what if that's the one I want? What if I want the XY plane? How do I differentiate the fact that given this plane, I'm sorry, given this point, I want this plane? Well, imagine I had a hammer and a nail. I'm going to nail the yellow plane down through this point. And that way I'm going to hold it steady. That plane I'm going to hold that plane, that yellow plane, flat and steady by nailing it down through this point. Well, what's true about my nailing down? What direction am I nailing in? Perpendicular. What is the N word that we used for that? Normal. If you have a normal vector through a point, that defines the plane. The normal nails down the plane that you want. I know that's kind of abstract, but let's just go through it mathematically first, and then I'll show you what I mean. So, what do I have to have in order to find the equation of a plane? To find the equation of a plane, I don't need a point and a slope or a point and a direction vector. I need a point and a vector that is normal to the plane I want. So let's just do this abstractly at first. So let's suppose I have a normal vector ABC, and I have a point that is known, 1, 2, 3, negative 4, 5, 7, 0, 0, 1, 1, 0, 1, right? Whatever This is a known point. So, and this is your hammer. This is the hammer you are going to nail through that point. But I want to know about, that's just one point. What about all the points on this plane? What's true about all, if indeed I am any point in this plane? So let's suppose instead of my generic, and let me change, so I'm calling this D, E, and F. This is a known point. And I'm nailing the normal vector through this point. But what's true about any point in this plane? Any generic x, y, z. Remember, vectors can be moved around. So isn't this vector perpendicular to all of the points as long as they're in the yellow plane? How does that help? Well, first let me build a vector from the known point to a generic one. So I'm going to go along in the plane. So I'm going to pick any generic point and go from my known point to this plane, to this one. Right? So there's a vector. I'm going to build that vector. What's true about the black vector and my hammer? They're perpendicular, right? Isn't that true if I chose this random point? As long as I go from my known point over to this point and I create that vector, if I create that vector, this vector, any vector, isn't it true that any vector radiating from my known point out to any xyz in the plane that I'm after, all of those vectors will be perpendicular to the normal vector that I have, nailing my hammer. Right? So remember, this is known, and this is any point in the plane. So, how do I create a vector, right? This is old news. X minus D, Y minus E, Z minus F. Right? You know how to do that. We've done that before. So, and again, in your mind, pretend this is, right? These are known, the D is a known value. Pretend it's, I don't know, 2. Pretend E is 3. And pretend F is -1. Right? The distance from any X in the plane to D, any Y in the plane to E, any Z in the plane to F. What do I want to be true about this vector? That's the black vector. What do I want? What's true? Right? What's true about this vector? Right? These are all the black ones. These are the black vectors in my picture in the yellow plane. What is true about all these black vectors and my hammer? What did we say is true? All of these black vectors in the yellow plane are perpendicular to the normal through the given point. Well, what do you know about two vectors that are perpendicular? What is true? Think about something we've learned to do with vectors. That's right, you got it. Their dot product must be equal to 0. So let's do some math here, right? Let's do some math. How do you do the dot product? The dot product is the x component times the x component added to the y component times the y component added to the z component times the other z component. So a times x and d with a minus, b times y and e with the minus, c times z and f with the minus. Now remember, this term, and this term are really going to be numbers, right? Because once I have a normal, somebody's going to give you the normal vector, and it's going to be whatever numbers are in here. So A, B, and C, D, E, and F are numbers. So I want to take all three of these numbers and move them over to the right side and combine them. So I have three numbers on the right side. I'm going to put them together. They're all just one number, one constant. And then look at these. What is A, B, and C? What are those? Whoop, 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 whoop. They're numbers. But what are they numbers of? Oh snap, the standard form of an equation of a plane has the normal vector in it. That's so cool that when we write out the equation for the plane, we capitalize those. So A, B, and C are the x, y, and z components of the normal vector, and D is just a number, and it is a number that came from doing this math here, doing the dot product and collecting everything that was a number on the right side. There are times when you will see, and sometimes I'll write it this way as well, when sometimes, just like if you remember the standard form of a line, right? Sometimes you will see this. Right? They'll keep the 0 on the right side and put the constant over here. Again, it doesn't matter. I know it's a negative D. If I move this literally over here, I change the sign. But since this is just a constant, if it was negative, I just say plus a negative. So nobody freak out there about that. So here it is in form, right? If you want to write that down. And normally this is only capitalized because they're capitalized here. So let's play around with this applet for a little. I promised you I would do a visual. So do you see? So right here is a point, right? A point in space, right? That looks like, right? It's in the, right up here. But I can move that point around. No matter where I put that point, look, it doesn't change the orientation of the plane, right? No matter where I put that point, because I've nailed it down. Here's the, right? I hammered down, or hammered up through, however you want to think about it, through this red point. Right? And as long as this is my normal, if somebody has given me this normal, no matter where I put this point, right, my plane doesn't change its orientation. But if you change the normal on me, right, if I go directly opposite, it doesn't change. But look, I can make this go straight up. Right? I mean, there's the XY plane. Right? You see I've nailed it down, absolutely perpendicular. Right? My hammer was down the z-axis and I nailed through the origin. Right? Again, if I move, right, move the normal around, it changes not the location of the point, but the orientation of the plane. So that's why you need a point. Where is the point? And then what direction are you nailing through the point? that nails down your plane. That's why you need a point and a normal. Kind of cool, right? So let's practice. Can you write the equation of a plane that goes to the point 1, 5, negative 2 with this normal vector? So what do you have to do there? Right? This is pretty much just plug and chug through right through the formula. I already know what A, B, and C are, right? A, B, and C. So I can at least, even if I don't know what to do, I can get partial credit, right? If I'm not completely not sure, as long as I remember that part. 1x, which of course I don't have to write the 1, minus 2y plus 4c is equal to d. So all I'm looking for is d. Whoops, I forgot to write my z there. Right, so I've got that far. So what do I do now? Right, think about the math that we did. Right, we need the point in the plane. We need to know how we're nailing down the point. But remember, we need our generic point in the plane. So we're going to say x, y, and z is any other point in the plane. And the first thing we're going to do is create that vector, right? Those are the black vectors in that yellow plane. Right? And then we'll look at it. So we're going to say, I don't know why I erased that, my generic x, y, z. So I'm going to create a vector going from the point 1, 5, negative 2. So it's kind of like that's my point, that's my A or my D. Right, going from here to here. So what am I going to do? X minus 1, comma, y minus 5, comma, z plus 2. And what does that have to be with the normal? Right? And then we're going to have the normal 1, negative 2, 4. And what do we say was true about every vector in the plane that I want? Has to be perpendicular to the normal. And to get perpendicularity, the dot product needs to be equal to what? 0. That means perpendicular. So let's do the dot product then. One times x minus 1 minus 2 times y minus 5. I just like to put the multiplier first, right? You don't have to. Plus 4 times z plus 2 has to equal 0. I can't even read my writing. Is that an 8? So remember, you want to take all the numbers and gather them up. So just the regular numbers, number, number, number. So I have 18, right? 8 plus 10 is 18, minus 1 is 17. So positive 17 moved to the other side means I'm going to have a negative 17. And that's going to be equal to, I should only have x's here, x minus 2y plus 4z. And now check with that first thing that we wrote down. right? Remember we had the 1, the -2, and the +4, and we were just looking for our D, and oh, we found it, right? So, what was my procedure, right? When they're asked to write an equation for a plane through a point, when they gave me the point and the normal, right? Get your generic XYZ. Generate a vector in the plane with the given point. And I'm going to use x minus x sub 1 for the given x, right? And that's what I did up here. Right? The 1, 5, and the -2. Third, I did the dot product. Take that vector and do the dot product with the given normal. And then simplify. Right? So here was step 1. Here was step 2. Well, I guess really all the way over to here was step 3. Right? And this is also step 3 when I actually wrote out the dot product. And then here was step 4 where I cleaned it up. Let's take a look at this. Right, so right now I just have the point floating in space here, 1, 5, -2, right? And this is the vector I was given, right? Just goes right out from the origin, the vector 1, -2, 4. And here's the plane that we found. I'm going to turn the plane on, and now you can see that certainly our point is in the plane, and that this is my vector. Now this is a little misleading, just the way GeoGebra works, right? I don't show this continuing or the vector over here going through this point, but hopefully you can see it is perpendicular to anything I would draw, right? All the vectors to any XYZ I would draw. So for instance, if my other point was over here, right, and I drew this vector, right, it doesn't matter where I go on this plane. And maybe if I do this, what if I shrink this to, let's see, right? If I make the point that I wanted to go through 0, 0, 0, you can kind of see, right, the normal is there. And all this D does, right, is shift this plane up or down through, you know, it just, I would have a different equation, obviously, as you can see, because this blue plane doesn't go through my point. But all I do by changing this value here, right, I don't change the direction of this plane or the orientation of this plane at all. So it is still perpendicular to this vector, and any vector within this plane is perpendicular. If you can imagine clicking and dragging this vector anywhere, or any vector being drawn through here, right? Crazy Rack Funky. Cool. All right, let's throw you a little bit of a curveball here. What if I don't give you the normal? What if I just give you 3 points? This is kind of analogous to in Algebra 1 when instead of giving you a point and a slope, I gave you 2 points. So you had to use the points to find the slope, right? Hold on, I'm sorry, I'm answering a text. So I've captured a picture here that I can draw on. of these 3 points, P, Q, and R. It doesn't matter which one you start with. If I choose to start at P, let's say, and I make this vector, which is an old objective, I know how to get, right, given 2 points, write the equation, right, get that vector, and I do this one, right, that's going, now that gray is just, that's just the floor, right? So what I want with these 2 vectors, I want the plane that contain these 2 vectors. But again, there's infinite amount of planes that contain, right? Well, I mean, these 3, there's only one, but I want to write the equation of it, right? It takes 3 non-collinear points to determine a plane. So what do I need though? In order to write the equation of a plane, I need a point. Well, good, I got 3 of them. And what else do I need? I need the normal. So if I need the normal, right, what operation have you learned before that will get you the normal going through, let's say, point P? And it doesn't matter which point I choose, but if I chose point P, right, what is that? I think you know. So step 1, I do have to build those 2 vectors, right? I have to build them, but I know how to do that. So building those 2 vectors means PQ is what? Right? -7, 5, and -1. Check my math on that. And now again, this is translating them all like to the origin, right? And then I'm going to do PR. PR, right, is just 2 minus 3. 2 minus 0 and -3 minus 2. So if I'm doing my math right, I get -1, 2, -5. 2 minus 3, 2 minus 0. Yep, that's right. And then those 2 vectors, what do I need? I need a normal. I need another vector normal to these 2. Who gets that for me? Yep, you got it. The cross product. So remember, the cross product comes from a determinant. And it's a 3 by 3 where I, j, and k I can't tell you how often you're going to use this in multivariable and in IBHL. You won't be doing much of this in BC calculus, because BC calculus is single variable calculus, right? So it stays pretty much in 2 space. So you're not going to have to do any of this till you get to beyond single variable calculus, which is either in multivariable, and then again IBHL touches on a bit of it. So that's why it's important to keep organized notes, right? There are things on IB exams that you're going to need from AAF, from IB pre-cal, and from BC, right? It really is a 4-year progression to get to the IBHL exam. And if you're doing the IBSL exam, you need stuff from AAF, pre-cal, and AB calculus. All right. So remember, this is, there's different ways to do, and and this is such an easy thing to Google. If you Google doing determinants of a 3 by 3 determinant. This is just how I organize it. So what do I get here, right? This is right. I'm going to go through this quickly because this is an old objective. So I ended up with a -23. Out of this, and a -34, and a -9. Right, so that was my normal vector. And then what do I need to do? Right? Then what I need to do is what I did in the last line. Find the equation of the plane using a given point. Doesn't matter what point you use. And this normal vector. Right, if I just use the first one I'm given and the normal and do what I did on the previous slide. So remember, I'm going to take a generic XYZ with the given point, and I'm going to build a vector. So I have x minus 3, y minus 0, and z minus 2. And I'm going to dot that with the normal that I just found. So much negativity in that normal vector, huh? Womp womp. And I did, right, I'm not going to go through that step-by-step algebra. I'll leave that to you. I ended up with negative 24x plus 69 minus 34y minus 9z plus 18 is equal to 0. Cleaned all that up and I got negative 24x minus 34y minus 9z and was equal to negative 87. Now, this answer here is perfectly fine for anything for us, for anything you're writing a free response answer to. If this was a multiple choice, I need to tell you that most often they look to try to reduce those coefficients and to not lead with a negative, right? They don't like the negativity. So there are no, I don't think there's any common factors here, but you could see this written as positive 24x, positive 34y, positive 9z, and positive 87. Right? Again, you are not responsible for that. I just need you to know, to recognize if anybody writes it that way to you or it's in multiple choice. All right? Okay, check. That was another objective. All right, now this one I think is a little bit harder to visualize, and if you've maybe got two pieces of paper that you can kind of hold and represent two planes, it might help you. But this was the formula that we had given you before for finding the, remember, and I proved it for you where it came from, finding the angle between two vectors. And then we usually, and most often in degree mode, we actually went from here to actually using inverse cosine, right? And you would use your calculator and you would get that usually in degrees. But again, just read the context of the problem, whether they are talking to you in degrees or radians, and if they don't mandate that, you can do whichever one you want. So the formula for finding the angle between two vectors, right, is that, but what if I want to find the angle between two planes? So there's like two pieces of paper, almost like a book, right? But notice the lines that are drawn on each one. It's almost the same formula, because do you see that using the, right, the equations of the normals, this is the normal, this is the normal, you know, a line in one plane versus a line in another, where do they intersect? Right? This angle here. Right? And this line is normal to this plane. Line 2 is normal to plane 1. So if you're holding two pieces of paper together, And if you can, right, can you hear mine? If I'm holding two pieces of paper together, kind of sort of like that picture, if you move the top one back and forth, you can kind of see, right, a very small angle as they approach almost being coinciding, right? They're the same plane. And then I can get all the way, of course, to 90 degrees. But what happens when you go past 90 degrees, right? Move your paper so that it's in the middle of the other. One paper is in the middle of the other paper at a 90-degree angle. Right? Can you see that really, as soon as you're looking on one side and you go past 90 degrees, the other side has the supplementary angle, right? So, in other words, I don't really, the angle between the planes is always going to be acute, right? Because no matter, even if I take this one and swing it back here, because planes go on forever and ever and ever, I only care about whichever angle. I don't care where that angle is relative to plane, just I want the acute angle. Now think about what I had up there before, right? What I had up here was how we actually compute this is taking the inverse cosine. What, right? Remember the restrictions on inverse cosine? Right? Inverse cosine only gives you results in which two quadrants? Right? Cosine is always positive in quadrant 2, and that's when, if I'm going from quadrant right on my unit circle, if I'm going through quadrant 1 here, right, those are only acute angles, and as soon as I go past 90 degrees, that's where I'm going to get quadrant 2 angles. So I don't need quadrant 2 angles. I only need inverse cosine to give me an acute angle in quadrant 1. But notice that these are just numbers, right? These are the magnitude of u and v, right? Magnitude of u and v, right? That's not a determinant, right? You need to know that I know the notation is very similar, but when you see it like this, that's the magnitude of u, which is Pythagoras, the magnitude of the second one, and then this is the dot product. Well, the dot product can be positive or negative, can't it? Well, what if I only want positive? What am I going to do? Oh, snap. So this is the formula for the angle between two planes. It's the same as the angle between two vectors, but you put an absolute value bar around the dot product, around the numerator. This was a little hard, and I know me rustling papers and telling you, right, and telling you to hold one and move it or whatever is a little confusing. So this is a hyperlink right here. If you, this PowerPoint is on Canvas, and if you click this hyperlink, it'll take you to a YouTube video where there's a guy, a video of a guy demonstrating this, right, and talking about this phenomenon and why you need just the dot product, and he draws it a little bit better than me, right? So, and doesn't rustle papers in your ears. So just use that if you need a little bit more visual as to what that means. But in the meantime, you can just memorize this formula. So if I ask you to find the angle between these two planes, right, what am I going to do? First thing I need is the dot product, right? Oh, what's wrong with this one? Oh, trying to trick me, eh? Trying to trick me, eh? Move that z over there, right? So this is really 2x plus 3y minus z is equal to 4. I do need to be in standard form. So the first thing I'm going to do is the dot product. And I'm going to dot 2, 3, and negative 1, you tricky kids. Dotted with 5, negative 2, and negative 1. I did that dot product, and I got 4. Check my math on that, right? 10 minus 6 and plus 1. Oh wait, this is a 1. Sorry, that's not right. Thank you for checking my math on that. Ah, I didn't mean to raise it all, gosh darn it. I'm dotting 2, 3, negative 1, dot 5, negative 2, negative 1, and I get 10 minus 6 plus 1, not plus 0, you dippy. So I end up with 10 minus 6 is 4 plus 1 is 5. Then the next thing I need, right, is the magnitude of u. And the magnitude of v. And I got the square root of, is that 10, 14 times the square root of 30. Now I'm going to inverse cosine the absolute value of the dot product, which I don't need because it was positive to begin with. Oh dear, right? That might just make you mess with your head, right? Because I'm using absolute value bars, huh? I didn't even think about that. Right? This is not the magnitude, that's absolute value. Over the square root of 14 times 30. And when I did this on my calculator, I got something, but I didn't write it down. And I'm looking for my calculator. And I don't know, oh, here it is. So I'm in degree mode. And I'm doing inverse cosine of 5 divided by the square root of 14 times 30. And I got 75.9. Okay. Good. All right, almost done. I'm going to go ahead and erase this. These two lines, I'm sorry, these two planes are parallel. Question, can you tell? Right? Well, what do you think it means for planes to be parallel? Right? Think about these two planes up here to be parallel. Like, what if you flip this all the way down, right? Then what would be true about this vector compared to this vector? Right? If you either laid them on top of one another or flipped it so it was at 180 degrees, isn't it true that, right, the normals would be scalar multiples of each other, right? So where are the normals? Oh, hello. Hello, normal one. Now remember, this is not in the plane, right? This don't get confused with this. The L1 is normal to the second plane. L2 is normal to the first plane, right? This is plane 1. This is plane 2. L2 is normal to plane 1. So what's true about the normal 2, 3, and 6? Is it a scalar multiple of x, 1, 3/2, and 3? And again, you can put the scalar here or here, it matters not. The way I've done it, the way I've written it, isn't it true that if you put a 2 here, 2 times 1 is 2, 2 times 3 halves is 3, and 2 times 3 is 6, right? Conversely, are these two, so I told you these planes were parallel and just asked you to verify. These ones, this question is, are they parallel or perpendicular? And tell me how you know, and you can just tell me in math. Well, the first thing I'm going to do is say, well, is 2, 3, -5 a scalar multiple of 4? Nope, I can already tell, right? Can you? No, there is no scalar multiple that takes 2 takes me to 4, but then multiplying 3 by 2 doesn't get me 6, and 3 times -5 certainly doesn't get me 4. So not scalar multiples of one another. How can I tell if they're perpendicular? If what? Their dot product is equal to 0. So is this dot product equal to 0? 4 times 2 is 8, plus 12. Well, that's 20, so the next term better be equal to what? I mean, the next thing in the dot product, in order to be perpendicular, must be -20, is it? Yeah, it is. So the justification is, just tell me in words what the math you just did. Don't just say the words, right? Do the math and the words when it says justify. Okay? All right, that's it. Your homework.
No homework.
Again, shut up, Dylan. Optional for now is a handout, and that handout is on Canvas, and it says equations of planes, right, with solutions already there. All right, have a good one, and I will talk to you next week sometime. Take care of you and your family.